Just as we have operations between numbers like addition, subtraction, we also have operations that we could do between sets. The first of these operations is the union operation. And the union between, let's say, just two sets, between A and B, will give us a new set. The union between A and B is a new set. We could call this set C, which contains, so set C will contain the elements or the objects in A or in B or both. So we denote this operator, union, by this symbol, which we call cap, which just looks like a capital U. And the union between A and B will be denoted like this, and it gives us a new set C. As an example, if set A had these objects and set B had these objects, then the union between A and B would be all the elements or all the objects that are in A, which are 0, 2, 4, 6, or in B, which are 1, 3, 5, and 7. And this is a new set, which is C. Obviously, we don't have to name it C. We can name it any other letter that we want, but just to go in order from A, B, and C. Now, let's do one more example of a more complicated set. If I had a set A that was a two-dimensional set containing the points x and y, such that x was between 0 and 1/2, and y was between 1 and 3, and I had a set B which contained all the points x, y such that x was between 1/2, including 1/2, up to 1, and y started at 3 and went up to 4, then the union between A and B would also be a two-dimensional set containing the points x and y, but this time we need to combine all the elements in A or in B. Starting with the x values, to combine this interval and this interval, we see that all the points in set A span from 0 up to 1/2, not including 1/2, and then starting in set B, we're containing the points including 1/2 and then going up to 1. So if we were to combine all the x elements in A and all the x elements in B, that would give us the interval from 0, including 0, up to, but not including 1. And this interval makes sure that we include this 1/2, which wasn't included in set A, but was included in set B. And similarly, for the y interval, we will start at 1 and span up to 4. And this is our new set, C. So that's the union operation. The second operation we could do between two sets will be called the intersection. The intersection between sets A and B, between A and B, is also going to be a new set C, which includes the elements or the objects that are common, or yeah, that are common to both sets. And we denote the intersection operator by the cup, or this might be called the cap, and this is the cup, or just an upside down U. So this is the intersection symbol, and we denote the intersection between A and B like this. Okay, let's look at two examples for the intersection. Maybe three examples. If I had a set A that contained the objects for the set containing these numbers, 7, and maybe another set that contained the number 1, and I had a set B that contained 3, 2, 1, and 8. Let's add one more object, 4. Then the intersection between A and B is going to be a new set C, which is a set that contains all the elements that are common to both A and B. So which elements or which objects are common between A and B? Well, 4 is, right? Because 4 is in A and in B. 3 in B is not, because it's not in A. So isn't 2. This set isn't anywhere to be found in set B. This object is found in A though. And that looks to be it. So they share two objects in common, and those are the objects that are going to be in the intersection. So it's going to be the number 4 and the set containing the number 1. Okay, let's look at another example where we have a set, let's call it D, that's going to be a three-dimensional set containing the points x, y, and z, where x is going to be between 0 and 1, y is going to be between 2 and 4, and let's move this over, and z is going to be between -1 and 2. And if I had a set E that was also a three-dimensional set whose intervals were these, let's do 3/4, then we could have 3, then we could have 4 here, and then maybe 0, z up to 1. Now the intersection between D and E is going to be a new set, let's call it K. It's also going to be a three-dimensional set such that we need all the points that are in common, or all the values that are in common in both sets. Starting with the x interval, we see that this interval happens to be a subset of this interval, which means that the intersection of all the x values here and all the x values here will actually just be this interval. So their intersection for the x values will just be this interval. Likewise, for the y values, this is a subset of this. So their intersection will be exactly that second interval. And similarly, this is a subset of this. So it's just going to be that interval. And if you notice something, their intersection just happens to equal set E. So set K and set E are equal, and we got set K by intersecting set D and set E. Seems interesting, and that's actually because we have a special case here where E is a subset of D, right? Because all the elements or all the points in E are points in D. So E is a subset of set D, which means that their intersection is just going to give you E, which is pretty cool. As in the last example of the intersection, let's look at a set G that contains two simple objects, 1 and 2, and a set H that contains 3 and 4. Then the intersection between H and G, well, what objects do they have in common? Seems like they have no objects in common. Then that means that their intersection must be empty because it contains no objects. Oh, and that's just the empty set. So with intersections, you could actually have an empty set because two sets may not have common objects. Let's go over two properties that both the union operation and the intersection operation have. They're both commutative or commutative, however you pronounce it, which simply means that it doesn't matter if we take the union between A and B in this order or in this order. They're going to give you the same results. And the reason this is true goes back to how we define equality between two sets. So remember, this gives us a new set, C, and let's call it C1, and this will also give us a new set, C2. And we're saying that it doesn't matter if we're taking A union B versus B union A, it's going to give us the same set. So we're basically saying C1 is going to equal C2. And the reason this is true, going back to the definition of equality between two sets, it just means that C1 must be a subset of C2 and C2 must be a subset of C1. And we could prove that this is the case for the union operator. But we don't have to. It's just good to know that it's true. Another property that the union operator has, I should also mention the intersection operator is also commutative. So A intersect B is equal to B intersect A. So these are both true. They're also both associative. So if we had three sets, A, B, and C, then taking the union between B and C first and then taking the union of A is going to give us the same set as taking the union between A and B first and then taking the union of C. And this is also true for the intersection operation. Okay. Maybe it's worthwhile to actually prove one of these properties. So let's prove the commutative property for the union. So let's show that A union B equals B union A. And again, how we're going to prove this is we're going to prove that if we choose any arbitrary object in this set, then it must also be in this set, which will allow us to say that this set is a subset of this. But also we have to show that, okay, is the reverse true? Is this a subset of this? And the way we show that is, again, picking an arbitrary object in this set and showing that it will also belong to this set, making this a subset of this. And then once they're subsets of each other, we can say that they're equal. Okay, let's try to outline this proof. So let's pick an arbitrary object, X, and let's say it's an element of A union B. Okay, well, what does this mean? For an object X to be in the union between A and B, it means that X is in A or X is in B, right? By the definition that we gave all the way up here. Okay. Well, if X is in A or X is in B, then X must be in B or X must be in A, just reversing the order. Oh, but this just implies then, from the definition of union, if X is in B or X is in A, then X must be in the union between B and A. Thus, we can say, because X is in A union B and X is in B union A, we can say that A union B is a subset of B union A. And if we follow the same logic, we can also show that B union A is going to be a subset of A union B. And these two implications mean that A union B equals B union A. And that proves the commutative property of the union operation. And you could do a similar proof for proving this property and these properties for associativity.